Hi guys, and welcome to our Wadix Technologies YouTube channel. Wadix Technologies is a company specialized on embedded systems training and online coursing. We offer a big variety of free online courses specialized on embedded systems technologies. All of this is within our YouTube channel. We provide as well blogs, articles, advanced online courses, and one-to-one training services specialized on embedded systems technologies within our website www.wadix.txt. So don't forget to hit the subscribe button of our YouTube channel, as well as checking out the different services we offer within our website wadix.txt. Hi guys, and welcome to today's course. In today's course, we're gonna cover and go through the CMake build system generator. We will see the main features supported by our CMake build system, as well as the different keywords, syntax, and built-in functions used within the CMake. We'll be able to see how we can use CMake to generate a full complete backend makefiles based build system. And finally, we'll be able to write our first embedded system based application that use CMake as build system generator. So welcome to this course. Within the scope of this course, we're gonna see the added value of using the CMake as build system generator. Added value compared to the manual way of building a complete embedded system project, as well as compared to the usage of Make build tool as only tool to build our project. We'll go through the main features supported by our CMake build system, like cross-platform support, multiple toolchain handling, and so on. We will see those features one by one, like the support of cross-platform compilation and building, the ability to use CMake to generate a complete backend makefiles or Ninja build system. We'll go as well through the different syntax, keywords, and built-in functions supported by our CMake. And finally, we'll be able to deploy what we have learned to write our first embedded systems project that use CMake as build system. An embedded system-based project consists of set of sources, headers, and of course linker script. And the main idea is to generate out of this project a single binary that will be loaded into our embedded system device. To go from this set of sources, header, and linker script to having a single binary, we'll need to go through the build process to compile the different sources and link them to generate this final binary. The whole idea consists of compiling the different sources one by one to generate out of them the different object files. And then, during the linking stage, we'll link all those objects to generate this final binary to be loaded into our embedded device. However, if we'll have a big embedded system based project, this means as consequence we're gonna have a big number in terms of sources and headers, and hence trying to build all those sources one by one to generate the different objects by manual way is gonna be kind of painful and time consuming. And of course, it will cause a lot of errors and problems to track the different issues that may appear. Hence, we'll need a tool or a mechanism to automate this build flow. And this is the idea behind tools like Make as well as CMake build system generator. So Make or Ninja or CMake, all those tools and build systems generators are used mainly to automate this build flow of our project. And hence, we are abstracting to the user the way of building the different sources to generate the final binary. Now, beside automating the build flow of our embedded system project and abstracting to the user the way of generating this final binary, CMake has another added value compared to the standard tools like Make. CMake is considered as build system generator. So by itself, CMake is not a build tool. So it is not the one to trigger actually the compilation of the different sources as well as the linking of those objects. No. The CMake will process an entry point file to generate a list of makefiles or Ninja files, and those ones will be the actual build system, and this one will be used as well to trigger the compilation of the different sources and generate the final binary. Hence, the CMake is adding extra layer before even we generate those makefiles. So instead of writing the different makefiles by ourselves and managing the different makefile rules dependencies by ourselves, we automate the flow of generation of those makefiles as well as writing those makefile rules using this CMake build system generator. So we program the high-level rules and dependencies to CMake, and we provide our inputs on what will be the different sources to be used, as well as the expected output, and then we trigger the execution of our CMake. The CMake, based on the different inputs that has been given, including, by the way, which build tool to be used to compile. So we can use Make or Ninja, and Ninja is another build tool similar to Make. Based on those given input, the CMake will generate the proper files that will work with the chosen build tool. So if we have chosen to generate makefiles based files, then the CMake will generate makefiles. Then, based on the list of the sources and expected outcome, the CMake will handle in automated way the generation of the different makefile rules, and it will write those makefile rules and different dependencies between those rules within our list of makefiles. In other words, the CMake is handling the generation of a full complete makefiles based build system. Then, as final stage, we will trigger the execution of our makefile rules by triggering the make build flow. And then those rules will take care of compiling the different sources, generating the different objects, linking them, and generate the final binary. Now, if we try to do a kind of quick benchmarking between our CMake build system generator and our Make build tool, the first thing to say is that our CMake can be considered as complete build system in respect to our make. CMake does offer a lot of built-in functions and features that allows, for example, handling of the different files and folders management. Means we can, with those built-in functions, create directories, remove directories, we can move files from one location to another, and so on. This is not possible with Make. We will need to invoke external applications and tools to achieve those kind of functionalities. As stated before, CMake is build system generator. So it is not CMake that will create those dependencies between the different rules to be able to compile our source files, generate the different objects, and link them. No. The CMake will automate the flow of the generation of the different makefiles, and those makefiles that will embed the different dependencies between the rules to compile our sources. And this is why the CMake is called as build system generator, because it generates as backend the list of the makefiles that embed the different rules to compile our sources. After generating the list of the makefiles, the CMake will trigger the compilation of our project by invoking make, and this is done on backend. So the generation and the invocation of the make, all of this is abstracted for the user. So as stated as well, it has a lot of built-in functions to handle files, like copying files from one location to another, removing files, and so on. Nevertheless, there is one drawback, I see it personally with the CMake, is that it doesn't offer that low-level control over the backend rules generation. It is correct that it automates the flow of generation of our backend makefiles and automate the creation and the writing of the different makefile rules. However, we rely fully on the way the CMake is resolving the dependencies between the different rules. And hence, if we want to customize things at this level, it will not be that easy with CMake. Make by itself is just a build tool. It will trigger the parsing of the makefiles and resolving the different dependencies to trigger the compilation of our sources and finally the linking of the binary. However, for any kind of file management and folder creations and so on, we'll need to invoke external applications and tools within our makefiles. However, our make offers a big advantage compared to CMake, which is better control over the different low-level rules and build flow. Here we are writing the different makefile rules by hand, not like here. And hence we can customize certain rules and dependencies to achieve certain functionalities and use cases. And this is not that easy to do if we rely on CMake to generate our backend makefiles. Now, we'll walk through the main features supported by our CMake build system generator. First of all, CMake has the support of cross-platform. Means our CMake-based project can be run either on Windows-based machine or macOS or Linux one. And not even that. We can do what is called cross-compilation of our embedded project. Means we can use CMake as build system of our embedded system project and run it within our Windows machine, but we are targeting different architecture like ARM. So the final binary that will be the outcome of this build procedure executed by CMake will be targeting an ARM-based platform. We can use the same project and execute it from a macOS-based machine. And similar here, the final binary will be targeting and executed on an ARM-based hardware. Same thing for Linux. We can do the same as well for an Intel-based hardware or architecture. So our final binary will be executed by an Intel-based processor. CMake does support what is called out-of-sources build. Out-of-sources means we'll have a separate directory out of our main project, and this directory will be acting kind of workspace for our CMake. So all compiled objects, temporary files, even backend make files, all of those will be generated in separate directory. And the final binary will be the outcome of the linking of those objects from the separate directory. So we are separating our workspace from the main project that contain only the different C and header files. It has automatic dependencies management. This means once the CMake is generating the different backend make files, it will handle the dependencies between the different makefile rules by himself or itself. Hence, we don't need actually to take care to create those rules and manage the dependencies between those rules. No, CMake will take care of generating the different makefiles, writing the different makefile rules to compile our sources, as well as handling the dependencies between those rules. It does support different toolchains configurations and cross compilations, as stated before. CMake allows as well generation of kind of template IDE projects. So it generates some IDE configurations, and those configurations can be integrated easily either like with Eclipse or VS Code. This means that we can instruct CMake during the backend generation to generate or create predefined configuration that can be imported, for example, by Eclipse. And once done, we can just start our Eclipse session and import this configuration. And this one will index the different sources of our project, as well as indexing basically some predefined debug configuration to start even debugging our project. Another feature which I like about CMake is that CMake is rich of built-in functions. So all of kind of file management, directories management, removing files, creating directories, copying files from one location to another, and many other functionalities are built in within CMake. So we don't need actually external tools or applications to handle those kind of things. All those kind of built-in functions can do such file management and directories handling. This is a block diagram to illustrate and demonstrate the support of what is called cross-platform compilation by our CMake build system. So our CMake based project can be executed and built on a Windows machine or a macOS machine or Linux one. So CMake does support all of those operating systems. Then either we generate a native binary that can be executed and run within our hosting machine. So for Windows 1, the final outcome is a binary to be executed by a Windows machine. If we run our project in macOS, then we are targeting the same hosting operating system. So the binary is expected to run on a macOS machine, and the same for Linux. But on top of that, CMake allows cross-compilation of our project. So we can generate a binary that is not targeting only Windows machine, but we are aiming to target a macOS one or Linux one. So this is possible as well. CMake, as I stated before, is not the one that will trigger the compilation of the different sources and the generation of the final binary. CMake is like an interface to trigger the generation of set of backend files. So it automates the flow of the generation of those files. And the type of files to be generated, it depends from certain inputs to be given to the CMake. So here the user will state if those files will be make based one or Ninja as an example. Based on this input, the CMake will generate either makefiles backend files or Ninja one. The makefiles one will be parsed and executed by Make, and the Ninja ones will be parsed and executed by Ninja build tool. So even the execution using Make or Ninja is automated as well by CMake. So the generation and the execution, both of those are triggered by CMake. Those files will embed the different rules as well as interdependencies between those rules to compile the different sources, generate the different objects, as well as linking those objects to generate the final binary. And it is not only about the final binary. We can also instruct CMake to generate the map files, some pre-processed files, and additional informations, and even executing some pre- and post-processing scripts. Beside the auto-generation of those build-based files, we can instruct CMake to generate certain predefined configurations, as you can see. And those configurations can be imported later on by the targeted IDE or tool. Means we can generate a configuration that can be imported by Eclipse. And this imported configuration allows Eclipse to index our project, means indexing the different sources, as well as starting a debug configuration and debug session on our project. Similar here, we can do the same for Visual Studio as well as Xcode. The main entry file or point that will embed the different instructions that tell CMake which build tool we are targeting, which IDE or tool we are targeting, as well as the location of the different sources, headers, the toolchain to be used, the target hardware where we are planning to run our application, all those inputs will be embedded and written within this CMake list file. So CMake will parse the content of this file to determine all those informations, and based on those informations, it will be able to generate the proper backend build files, the proper debug and IDE configurations, as well as generating and using the proper toolchain and target hardware. Now we are trying to illustrate here the CMake build flow in terms of build stages. So as stated before, the CMake will parse this entry file, which is our CMake list. And this file will embed informations like the toolchain to be used, the build tool and the format of the backend files to be generated, whether it is Ninja or Make's based one, the target hardware and architecture like ARM or Intel. We'll instruct as well to generate the build configuration and debug configuration as well as IDE configurations. Those ones will be targeting IDEs like Eclipse or Visual Studio or Xcode. So all of those inputs will be parsed out of this file, and the parsing and the translation of this input to kind of internal representation that CMake can understand, this is done at configure stage. So configure stage consists of parsing this initial CMake list, then translating all those inputs given by the user to set of internal representation and dependencies that the CMake can understand. And this will be written within this cmakelists.txt. Then later on, the CMake will fetch and read this CMake cache file and generate out of it the list of the native tools project files. In other words, here we're gonna generate those makefiles or Ninja backend files. Now we are taking this CMake enter representation, and then out of it we'll generate and write our backend build tool based files. So all those internal representations and dependencies will be translated to build tool based dependencies and representation. And then out of those files, the CMake will be able to trigger the build flow by running the proper build tool, whether it is Make or Ninja, against the corresponding generated build tool files, whether Make files or Ninja ones. And here, this will be our output binary files. Then we can even trigger the packaging of this output files to generate kind of CMake package. And this one we can release and provide to some customers. For the first stage, which is the CMake configure stage, the CMake, first of all, will check if we have already an old generated CMake cache.txt. If yes, then it will parse this file, then parse this cmakelists.txt, and then combine basically both inputs. So instead of writing this CMake cache from scratch, it will try to update it with the new content of our CMake list. This is one of the reasons, by the way, it tells you that if you update one of the .cmake files within your project, it is better that you start building from scratch, because you will be able to get rid of this CMake cache file. Now, once done, this CMake cache either will be updated if it does exist once we started our CMake build flow, or it will be created from scratch if it doesn't exist. And this one will contain and embed some internal representation that CMake can understand. So the initial build tree, as well as the list of the sources to be compiled, the internal dependencies that should exist between the sources and the expected outputs, all of this will be generated in kind of internal representation that the CMake can understand. So until now, we are still within the CMake context. We didn't move basically to the build tool context, and this is what we will see in the generate stage. Now, for the generate stage, the CMake this time will take as input the outcome of the configure stage, means the CMake cache.txt. Then, out of this internal CMake representation, which contains already the different dependencies between the input files and sources and the expected output objects and binaries, it will generate the files and backend build tool files that will embed the real implementation and representation of those dependencies and rules from the build tool perspective. Example, if we have chosen to generate and target a makefiles based build system, then the CMake will parse this CMake cache.txt, which embeds some internal CMake representation of the different internal dependencies, then translate this to a set of makefiles rules and internal dependencies between those makefiles rules. And then later, the CMake will invoke the make to parse the makefiles and parse the different makefile rules, and those ones will initiate the build of our set of sources, including the compilation of the different sources, and finally the generation of our binary. And then we can instruct, of course, CMake to generate a final release package. Now, in terms of syntax, CMake does support macros. Now, this is the way to define your own macro. You must use this keyword macro, and then you close the statement of your macro with end macro. And here, this is the name of your homemade macro. Now, the body of the macro can be anything, means it can contain, for instance, variable assignments as well as logging. Hence, you can create macros to log a specific set of messages, and then you can use these macros within any place within your CMake code. What we need to keep in mind is that macros does not support local scope, means they don't handle and preserve space within the stack, and hence we cannot have local variables within our macros. The macros can change the colors variables, means if we have global variables, use it within our CMake, then we invoke a macro, and within the body of this macro we modify this variable. Then this one will be globally modified after we finish the invocation of our macro. So this new value will be assigned by our macro. And this is simple because we don't have any local scope for the macros. So the scope or the internal scope of the macro is the same for the caller. And this is, by the way, different from the functions definition within our CMake. It's quite hard to debug macros. Now, after the CMake, let's say, get processed, and if we try to inspect the internal assemblies coming out of our CMake code, we'll see that all the macros will be aligned. So the body and the colon convention of those macros within the generated assembly code out of our CMake code will not preserve basically a standard function calling. No. Everything within the macros will be aligned and integrated as linear flow within our CMake assembly code. And hence, it is very hard actually to distinguish that this aligned assembly belongs to this macro. Another keywords supported by our CMake are functions. So we can create a custom function within our CMake code. So similar to macros, we need first of all to use this keyword function. Then we close the statement of our function definition by this end function. And here we place basically the name of our function. So really quite similar to the macro definitions. However, the major difference compared to macros is that functions, they have and support their own local scope. Means they do preserve space within the stack for local scope and variables. And this is totally different from macros. Because they have their own local scope, they don't interfere in general with the caller's variables. So we cannot, and in general, we don't need to change the caller variables within the function's body. The functions in general are not aligned like macros. And hence, if we inspect the generated assembly code out of the CMake code, we can see that we are jumping to our function, then out of our function once we are done. So the body of the functions are not aligned. And hence, they are much easier to debug and trace compared to macros. CMake does support as well if statement. And this is quite similar to what we have in programming languages like C or C++. Here, we'll place our if condition, and if it is met, then this command will be executed. The if statement within CMake does support else if as well as default statement else. And the most important thing here is that we should not forget to close the if statement invocation using this endif. On CMake, we can create a for loop to iterate over the different items and elements within our CMake list. And then we can use this item as input to the different commands within this for loop body. And similar to the if statement or the macros or functions definitions, we need to close our CMake for each loop by this end for each statement. And as stated before, the main goal is to iterate over different items within our CMake list. The concept of lists is supported as well by CMake syntax, and this is quite similar to what we have in Python. Means we can create a list of items And then we can manipulate those list of items within our CMake. Manipulating like searching through those items, deleting or adding new items, and so on. And by the way, this is very powerful feature supported by our CMake, because here we can append a list of sources to our makefile variable that will be passed later on to the compiler. We can append list of headers or any kind of file that we want to process. Another feature which is quite useful within our CMake build system is the usage of what is called built-in variables. Now, for globally and widely used paths, we can reference those paths like the location of the output binary or the top level directory of our project using those globally defined CMake variables. So, as an example, this CMake binary dir, this is refer basically to our global build directory. And this is the directory that will contain the different backend make files generated, as well as the different compiled object files and output binaries and so on. Now, if you have more than a single CMake list file, this means you will have more than a single workspace that embed the different backend files as well as the different objects and binaries. And this one is referring to the sublocation that will embed our local CMake list output workspace. Example, if you have your project like this, and then you have your top CMake list here, then you have another subdirectory like source, and there you have another local CMake list dedicated only for anything located within this subdirectory. Then the result will be like, this is your build directory. Now, the path to this build directory top level 1 is indexed by this variable, CMake binary dir. And this one will contain the workspace of our top level CMake list. This guy here will be located under build, then source, then here we'll have our local workspace dedicated as outcome of this processing of this CMake list. And this path from build then until this is referenced by our CMake current binary dir. Similar to the outcome result of our build flow, we can reference as well our top level directory of the source based project using those makefile variables, CMake source dir and CMake current source dir. This one reference basically the top level location of our main CMake list file. So mainly this is the path until we reach this top level CMake list. This one is referencing this local CMake list location. So project, then source, and here we go. So this is called global CMake list, and this is the local one, because it is one location under the top directory of the CMake. CMake build system does support wide variety of built-in functions. One type of those functions will handle the binary output generation. So functions like add executable will specify the name and the output of the binary to be generated, and thus specify the dependency in terms of sources and headers to allow the generation of this binary. Target include directories is another CMake built-in function, and it does specify the directory locations where we are having our headers files, and those directories paths are needed by the compiler to identify the location of those headers, and hence it will be able to compile properly the different sources that include those headers. Target link options will specify the set of linker flags and options to be passed to the linker. Similar, the target compile options will specify the set of flags and options to be passed to the compiler. And this is for the linker. And then during the configure stage, the CMake will parse the CMake list that will embed those built-in functions, and then create internal representations of the different sources, different headers, as well as which compiler and linker to be used, and the different compiler and linker flag to be used. And out of this internal representation, and during the generate stage, the CMake will create the list of the make files, and those ones will embed the different rules to invoke the compiler and the linker with the corresponding compiler flags and linker flags. So the initial informations needed to fill in those makefile rules and to use the proper command to compile our sources and identify the list of the sources and directories actually are given by those built-in functions which are invoked within our cmakelist file. The CMake built-in functions allow as well file management and handling. So we can copy file from one location to another. We can as well rename files, remove files, as well as expanding the files that ending with certain suffix to create list of files out of them. All of this can be done via this file CMake built-in function. In CMake build system, we will have in general a default build target, and this default build target will be matching and corresponding to our project or binary output. Nevertheless, we can add as well some custom target or custom build target to our CMake project. And hence, instead of building our default project, we can specify to CMake our custom or newly added custom target to be built. And this is done via this -- target. To add those new custom targets, we can use those CMake built-in functions, add custom target and set target properties. Now, beside adding those custom targets, we can also instruct CMake to execute some custom-made commands. And this is done by invoking this add custom command. This built-in function will allow providing set of outputs resulting from the command to be executed. Then we need to provide the body of the command or the application to be executed within the same API here. And even we can create the dependencies between this command to be executed and another previous command or some files to be generated. So as you can see, those set of built-in functions allow customizing the set of targets and commands to be executed by our CMake. And this is provide quite flexibility to the user to add his own routine and customized command. Now, to be able to start building our first CMake based project, we'll need a set of tools to allow generating our makefiles backend build files, as well as compiling and generating the final binary. Our CMake based project is an embedded system based one that is targeting an ARM based architecture. Means the output binary should work and run in an ARM processor. Therefore, we'll need first of all a tool chain that allow compiling the different sources and generate set of objects and the final binary that will be executed by the ARM processor. For that, we're gonna use the ARM GNU GCC version. Then we'll need, of course, our CMake build system generator tool. Then we'll need the GNU make build tool. We need this because the backend files that will be generated by our CMake will be set of makefiles. And hence, to be able to parse those makefiles and resolve the different makefiles rules dependencies, we will need our make build tool. I have provided all those tools as part of our Wadix technology tools repository. Hence, cloning and checking out this Git repository will give you access to all of those set of tools. So my first recommendation is to clone and check out the Git repository of our Wadix tools under C drive. With this way, we can shorten the path to the different tools to be used within our project. This is how your directory will look like after you have cloned the Wadix tools repository. Of course, you don't need all of those tools to be able to build your CMake based project. We need first of all the ARM GCC toolchain, and we need of course our CMake, and then we'll need as well the GNU make build tool. Once you have those minimal set of tools, you will be able to build your project. Another point is that we need to set up Windows environment variables to point to the different tool chains and tools. And hence, we'll be able to invoke and execute those tools and applications whenever they get invoked from the Windows command line. For that, I have provided, as part of the Wadix tools Git repository, those two PowerShell scripts, install and uninstall. This one will manipulate and update the different Windows environment variables, and to be more precise, the path Windows environment variable to point to the different location of our applications and tools needed to build the CMake project for ARM architecture. If you want to restore back the default setting, then you can execute this uninstall one. Now to execute this install PowerShell script, you will need to open a PowerShell session, then trigger the execution of this install environment PowerShell script. So here you can start a PowerShell session. Now, once the session is open, you will need to navigate to the location of your install script. Then, before the invocation of your install script, you will need to configure your PowerShell session to allow the execution of external scripts. To do so, there is a command that needs to be executed prior to running your script. So in this README, which is part of our tools repository, you can just copy this command to set the execution policy of the current PowerShell script to allow triggering the execution of external scripts. Yes to all. Then here you can safely execute your script. It may take a couple of seconds. It depends here from your machine, and sometimes you may need to reboot your machine. Here I don't need so I can just double check now the Windows environment variables, and to be more precise, the path one. So if I double click here, I see obviously that the location of the different tools needed to build our CMake project has been added to the path. So this is the location of our CMake. This is the location of the GNU ARM GCC toolchain. As you can see, this is the location of the Ninja build system if we want to use Ninja. This is not the case, of course, for our project. And this is the location of our Make build tool. If you want to restore back the default setting, then you can just execute this uninstall PowerShell script. We have prepared already a template for our CMake based project to demonstrate and illustrate what we have learned across the different slides. The project or template project will be provided as part of Wadix Technologies GitHub repository, and this is the link to the repository. The absolute link or path to this project will be provided as well as part of this course description. So don't forget to check out the description of this course video. Now, if you're gonna clone and check out our CMake based template project from the Wadix Technology repository, my recommendation is to do the cloning of this template project under C drive. This helps again to shorten the path to the different sources and CMake build files. The project is a complete one. It means basically just you can plug and play to compile it. However, this is not the main goal of this course. The main goal is to go through all the steps to be able to create and build your CMake based project. For that, you will need to remove everything if you want basically to start from scratch. So the idea behind this project is to give you kind of reference of the expected output after you have created your CMake project. So I am gonna remove all the files that I have created previously, and we can just keep the different C assembly files as well as the linker script. So the assumption here is that we have already an embedded system project, but we don't have an available build system to compile the different sources and generate the outcome binary. So here I will remove everything, and even I can remove all the files so that we start cleanly. So here we have only the sources and linker script, and we are missing our build system to be able to process all those sources and generate the different objects and finally the output binary. The first thing to be done to start building your CMake build system and integrating this build system as part of your project is to create the entry point to the CMake tool. This entry point will be our cmakelists.txt file. So during the configure stage, CMake will parse this file and update the CMake cache if it does exist, based on the new entries and updates coming from this CMake list. So having this file in the top directory level is a must to have. My second step will consist of creating a CMake subdirectory, and this one will embed the different, let's say, CMake toolchain configuration and build configurations. So here I can specify which toolchain to be used. Also, I can specify the different compiler flags, linker flags. I can even output some loggings and offer even some custom functions and macros implementations. So my recommendation is always to create a subdirectory that contains all those .cmake files. So this is create kind of isolation between our pure embedded C project and only build system related files. And finally, to invoke the CMake command with the proper input parameters, my recommendation is to create an abstracted bash script. This is for Windows, of course, to invoke the CMake with the proper input parameters. So if you have a custom target that requires this dash target, then you can invoke it within the build bash script. So instead of memorizing all those commands to be provided with the CMake, if we want to invoke this via the command line, then it's better to create a bash script and then we just double click to be able to build our project. This is offering an abstraction plus automated flow to trigger the building and the creation of our output binary. Hence, having this structure in place, as I stated before, create isolation between our embedded C project and the build system related build files. And also, it offers an abstraction and more automated way to trigger the build and the creation of our output binary out of the sources. So this is kind of plug and play concept. I will create now the different .cmake files to embed informations like the toolchain to be used, the different compiler and linker flags options to be deployed, as well as the CMake build type like debug or release, and many other informations. The structure that I'm going to show up is something that we use it to structure our own CMake build system, and it is not must to use or follow. Hence, feel free basically to create your own structure or reuse the structure that we are going to show up and shuffle things around. The first file to be created will be this CMake build configuration. So build config, then .cmake. Here I will be setting up and initializing some predefined global CMake variables. First of all, I will specify the build type, whether debug or release. Then I will specify the expected output location for our output binary. To specify the build type, I will need to initialize this CMake predefined global variable, CMake build type. It will be debug. Then I will cache this information So whenever we trigger a new build, the CMake will not update this information immediately. Then I will mark it as build debug. I can use the string to specify that I am doing basically a debug build. Now to set up the expected location of our output binary, I can initialize this predefined CMake global variable. CMake runtime output directory. In general, the location of the output binary should be under build directory. So the build directory will be the output workspace of our CMake build system. To reference basically this location, we can invoke as well the CMake binary dir predefined global variable. This one is referencing basically the path to our CMake build directory. Now to be more specific and to state that we want only the output binary to be located there, I will create a subdirectory within the build directory itself where only the output binary will be placed there. You need to remember that the build directory is kind of background workspace of our output CMake build flow, and hence it will embed a lot of files like the backend, makefiles, some objects files, and so on. So adding the output binary in top level of our build directory will be kind of messy. Hence, I will create this subdirectory bin, and therefore the CMake will just output and place the output binary under this subdirectory. The second .cmake file to be created will be the one that contain informations like the target system, which will be our ARM-based processor, the path to our toolchain, and the different executable out of this toolchain installation to be used to compile and assemble our different C sources. I will name this file ARM toolchain.cmake. First of all, I will set up which system we are targeting by our project. This helps basically to identify the target system to which we are compiling and generating the output binary. For that, I need to initialize some predefined CMake global variables like CMake system name, and here I will assign a generic name for it, and then set CMake system processor, and here it will be ARM. I will need right now to create and specify the path to the top directory installation of our ARM toolchain, as well as specifying the compiler or the C compiler, the C++ compiler, as well as the assembler to be used to compile and generate the different objects. First of all, I will initialize and create a CMake global variable that will hold the path to the top directory installation of our ARM toolchain. And then this will be the location or the top directory installation of our ARM toolchain. Then 10.3.2, then P. Then here I will need to initialize the predefined CMake global variable that are holding and specifying the path to the C compiler, the C++ compiler, as well as the assembler. This will be this guy actually. And then will be ARM non-EOP GCC. I need to do the same for the C++ as well as for the ASM. For the C++, I will need G++, and for the assembler, I can utilize the C compiler as a front end to process the different assembly files. After setting up and specifying the compiler executable and C++ executable to be used with our CMake based project, we'll need to specify the different compiler and linker flags options to be used. To do so, we can use either the CMake built-in functions like target compile option, or target link option, something like that, to set up those dependencies to those compiler and linker flags. And then the CMake will pass and propagate those compiler and linker options to be provided as input to the compiler and linker. Those options will be connected and used only for the target to specify it as input parameter to those APIs. Nevertheless, sometimes those APIs or built-in functions doesn't work perfectly with certain cross-compilation based systems. For ARM, we may and may not have the specified dependencies to those compiler flags and linker flag passed properly as inputs to our linker and compiler. Therefore, CMake has provided predefined global variables that set globally those compiler flags and linker flags. The only difference between using those predefined CMake global variables or those built-in one is that those built-in one will be used and associated with the target project or output binary to be provided as input to this API. Hence, we can have multiple output binaries, and we can invoke those APIs by target. Means we can invoke this one for output binary 1, then we can have another invocation for another output binary. And the specified flags will be used only for this target. And for the second invocation, we can provide a different set of compiler flags to be used with another output binary, and so on. However, those global predefined CMake variables used to set up the different compiler flags and linker flags are used globally. Means the different compiler flags and linker flags will be global and will be applied for the different target binaries. Means across all the output binaries, we will have and use the same compiler and linker flags. So as stated here, for certain cross-compilation platforms, those APIs are not working as expected. And therefore, CMake has provided and exposed those predefined global variables to set globally the different compiler and linker flags for our output binaries. In our use case, we're gonna use basically those predefined CMake global variables to set up our compiler and linker flags options. We will start by setting up some common compiler flags to be used with our C and C++ compilers. So I can create a CMake global variable to store the different CPU-based flags, and this will be specific to our ARM architecture. So here I will specify the CPU or target CPU. In our case will be Cortex-M4. This is just an example. Then I specify which FPU to be used. Here will be the FPU version 4. Then the binary interface of our FPU implementation. Basically, this means which library to be used for our FPU-based computing. Soft. So I'm gonna use some software implementation based binary to do some floating point based computation. Now those flags will be used with our C and C++ compiler. Here I need to invoke those predefined global CMake variable to propagate globally the different compiler and assembler flags. Now for C flags, I will need to set up this global CMake predefined variable. And here I will use, first of all, this locally defined CMake variable. Then I can append other compiler flag. So this to specify I want to have the debug symbols within our output binary, and this is, by the way, matching our build type, which is debug. This is the optimization level. Well, this depends really from your need. You can put it 0 if you don't want any kind of code size or performance optimization, or you can increase it based on your need. Here I use it O2. So I'm aiming to have, let's say, better code size optimization of our output binary. Same thing for our C++ compiler flags. So I will utilize the same C compiler flags. They should be similar. And finally, for our assembler, I don't need to utilize those CPU flags as they are not accepted, but I can, for instance, keep the usage of the optimization level and the big symbols. So here I was able to set up those predefined global CMake variables to propagate the different compiler flags to our backend compiler and C++ and assembler compilers as well. We'll set up now the different linker options flags to be passed to our linker. To do so, we can as well set up kind of CMake built-in global variable to propagate the different linker options flags to our linker. So the name of this built-in global variable is CMake X linker flags. Then I need to initialize this built-in global variable with set of linker flags to be passed to our ARM linker. So I can start by the name or target CPU. This will be Cortex-M4. Then I will need, of course, to specify the location and the name of our linker script. So this option is to be provided to our ARM GNU linker, and with it the linker will be able to know that we are providing right now our linker script. Now our linker script is located on the top directory of our CMake project under linker subdirectory. So to be more precise, it is here. So this is the top directory, and the top directory means the location where we are having our CMake list entry point. And this is our linker script. So to reference this top directory of our CMake project, we can invoke and utilize some built-in global variables, which is CMake source dir. This is pointing and providing the path to our CMake top directory project. Then linker script .lt. We can add as well some options to be passed to our backend linker. For that, we need to provide this -wl. This is stating to the ARM non-EOB GCC that any option coming after this should be passed as it is to our ARM non-EOB LD linker, so it will not be processed by the GCC. And here I can provide this input option, which is garbage collection sections. This is mainly needed to get rid of unused sections and hence optimize the size of our output binary. We will need now to create the sources.cmake file that will point to the different sources to be compiled. So this is our sources.cmake file. Here we'll need to create a global variable that will hold the list of the .c files to be compiled. So the name of the variable, I will name it like project sources. And here I should add and append the list of the sources to be compiled. First of all, I will need to provide the path to the different sources to be compiled. So, similar to what we have seen in setting up the different paths as well as compiler flags, I will need to specify the top CMake project directory. For that, I can invoke the CMake source dir. So the top directory will be the directory that contains the top CMake list file. Our sources are under source directory, and then the first source to be compiled is main.c. The second one will be our startup.s. And then we are done. So this is the list of the sources to be compiled. And this one will be provided later on to some CMake API to create the dependencies between the output binary and the list of the input sources to be compiled. We'll need now to create the headers.cmake file. So the headers.cmake file will contain the list of the headers to be provided alongside with the C sources during compilation. And we must provide the paths to the directories that contains those headers. The paths to those headers directories is must to have so that the compiler can resolve the dependencies to those headers while compiling the different sources. Headers.cmake. So here again, I will create some CMake variables. So project headers. Here I will create the list of the headers, use it within our project. So again, I need to point to the path of those headers. So I'm gonna utilize this CMake source dir to point to the top directory of our CMake project. Then enc, this is the location of our headers, and finally our header, which is device.h. So this is the single header basically used within our project. Then I will need to specify the directories containing those headers. So project include tiers, and the path will be this one. And we are done. So here I have specified the list of the headers, and this one, which is way important actually to provide, is paths to the directories containing the headers. This is to be propagated later on by CMake as input to our compiler, and this is the only way for the compiler to resolve the dependencies to those headers that get included within our sources. Not providing the path to the include directories where we are having our header will lead basically to compilation error. We'll start now coding our cmakelists.txt. First of all, we need to specify the CMake minimum required version. So version will be 3.15. It is not must to have it, of course, but it is recommended to have the check over the CMake version in use. Then we need to specify the project name. So this is the default target whenever we are invoking CMake to build our project. So here we're going to specify the name of our output binary. So my app.elf. Then I need to specify the type of the sources needed to compile this application. Here will be C, C++, CXX, and then ASM. It means we can have C sources, C++ sources, or assembler files. We'll need then to include the different .cmake files that has been previously created. You need always to keep in mind that the entry point for our CMake build procedure is this CMake list file. Hence, if we forget to include other .cmake files that embed other informations, then there is no way for the CMake build system to parse that .cmake and extract the necessary informations. And this, of course, may lead to some build failures. So include, then CMake, and then we start by listing our .cmake files. So we have build config, .cmake, then we have the ARM toolchain .cmake, then we'll have, of course, the sources .cmake, and finally the headers .cmake. Include CMake files. We will need now to invoke the CMake built-in function add underscore executable. This one will need to provide to the CMake the project name or the name of the expected output binary plus the dependency of this project name to the list of the input sources and headers. This is must to have so that the CMake can build internally the list of internal dependencies between the different makefile rules to be generated later on. So we need to specify the project name. So this will be the name of our output binary, and this has been specified here. Then we need to specify the list of dependencies in terms of sources and headers. We'll invoke the CMake variable that has been defined and initialized here in sources.cmake and headers.cmake. So project sources, and then project headers. And that's it. With this, our CMake will be able to identify the expected outcome from the build flow or procedure. Then we'll be able to create kind of internal tree of dependencies between the different sources and the output binary. We'll need now to specify the set of include headers directories to our CMake. So the CMake will need to propagate the list of the include directories to our compiler so that the compiler will be able to resolve the paths to the different headers included by our sources. To do so, we'll need to utilize the CMake built-in function target include directories. Then include the directories. Here we're gonna create a dependency between our output project name, and this will be actually the output binary, and then the list of the include directories. This list of include directories is already created and initialized within our headers.cmake. And this is the name actually of our global variable holding this list of include directories. Project include dirs. That's it. Now we have satisfied all the requirements to be able to build our embedded system project. We can add some messaging or logging via the CMake message built-in function. And here we can specify that we are building our CMake based project. And then we are ready actually to trigger the actual build of our CMake based project. After finishing writing our CMake code, we are ready to trigger the build of our CMake based project. To do so, we can create either a Windows command line session here, and we start invoking the commands to create our build directory, then invoking CMake with the proper input parameters to trigger the compilation of our project. The other way is to write all those commands within a single file called build.bat, and this is a bash script, and then we can just trigger and automate the creation of our build directory and the execution of the build by just double clicking this file. Of course, I am in favor of automating and writing all those commands within a single batch script. So first of all, we need to create a build directory. Then we need to go to our build directory. Once we are here, we can just invoke the CMake. Then we need to specify the style of the backend build tool files to be generated. In our case, will be makefiles. So Unix makefiles. Then we can specify the toolchain file to be used. We have the option to set up as well the CMake built-in global variable via this CMake command line. And this CMake built-in variable is used to specify the toolchain configuration file to be used as input to our CMake. And hence CMake will be able to know which toolchain to be used to compile the projects. So this will be CMake, then ARM toolchain.cmake. Then we go out again from our build directory, and then we invoke the build command, -- build from the current directory. And here we go. So once we double click here on this bash script, then we'll be able to see that the backend makefile generation will be triggered, and as well the make build tool invocation will be triggered automatically to build our project. Now we should be ready to start and trigger the build of our project. I will open a new Windows command line session on the top directory level of our project. I want to log the outcome results coming from the execution of this bash script. Hence, it will be easy for me to inspect any kind of errors coming from the CMake build flow. So let's trigger. And of course, we'll inspect any kind of errors coming from the build flow. Here we go. We have kind of typo and error in line 17 within our cmakelists.txt. So I go here, check line number 17, and this is our target include directories built-in function. Here I am missing basically one important key, which is private. This is kind of attribute to be assigned to our include directories. And this is specify if those include header directories will be only specific to this target or build target, or can be public. Public, it means any kind of CMake target or build target can utilize the same dependencies in terms of include headers. So here we can specify either private or public. In our case, it doesn't matter really because we have a single build target, which is our project. However, if you are having multiple target builds and there is kind of dependencies between those targets, then you may choose for certain build targets if the dependencies to their include directories will be private only to that target, or also it can be propagated to the other build targets. So if you choose public, then those include directories can be propagated and shared between the different CMake build targets. And private means those include directories are only private for this build target. In this case, I will put the keyword private, then trigger another build. So I will remove the build directory again, open a new Windows session, and then trigger our bash script. And here we go, we are done. And if we inspect the build directory, we can see obviously that this is our CMake output workspace. Those are the backend make files generated by our CMake build system generator. If we go here as well, here we can see a bunch of make files, as you can see this one as well, and the output binary will be located under build bin, and here we go. This is our application that can be loaded into our embedded device. So thank you guys for watching our CMake based course, and for more courses don't forget to hit the subscribe button of our YouTube channel, as well as feel free to check out our services and other online courses within our website wadix.txt.com. See you.